Good morning. Welcome to lectures 18, 19 of thermodynamics of materials. We are discussing reversible and irreversible adiabatic processes. Just we'll have some comments, a few more comments on that. So, reversible, irreversible, adiabatic. So this was the sketch. Let's recall. One A, two. This is a reversible adiabatic. This is what is the irreversible adiabatic. So 1A2 is 1A2 reversible adiabatic, while 1B2 prime irreversible adiabatic. Adiabatic. So this was discussed last time. So what we see here, the final states are not same. Remember, the system is n moles of ideal gas. The final states are not same. One is 2, another is 2 prime. Initial state same. Starting from the same initial state, the final states are different. This is exceptional case. In isothermal, there is no such problem. In isothermal, recall, compare isothermal. Reversible and irreversible, you will easily find what is the isothermal. Take a look, PV diagram on the PV. This is the isothermal, 1, A2, A2. And what is the irreversible? Again, you recall against the, if you mean note this, stop here. Stop there, 1, B2, irreversible. Take a double arrow to indicate. Why this happens? In constant pressure and constant volume processes, we will discuss today, the same. That final states, initial and final state are equal, are same. Means initial state for reversible and final states for initial states for reversible and irreversible, and final states for reversible and irreversible same. No change. But in this case there is change. Why this happens? Because this I said last day, so this actually shows adiabatic process. The final states are different. States of reversible and irreversible paths are different. This is special case. So this is a special case, exceptional case. What has happened here? The path, why this has happened? This is very strange. You may comment it. Comment. Comment is the path. The path has affected the state. Very interesting. The path has affected the final state. The path has affected the final state. Right here. Final states. Final state. Final states. Or final state. Affected the path. Path affects the state. So if it is reversible, this is the final state. If it is irreversible, this is this. If you consider another irreversible, it is still different. This actually, you have to, why this happens? dq, you might load this. dq is du plus dw. dq is zero adiabatic. So du, dw, or du is minus dw. This is path dependent. Interesting. dw is path, work function, path interaction, path dependent. For this argument, okay, comment, explanation, quick explanation. So the path dependent. So with path it changes. With path it changes. Du is a state property. So state, change in state. Change in state property, path, state property. So state property change is affected by the path. State property change, initial same. So which will be affected? Initial we have started with the same thing, same state. Final. This is the quick understanding. So this is a very, very special case, path affects. So this is happens, okay. Good. Isothermal, what happens? If you apply similarly isothermal, sir, do it for isothermal, sir. dq is du plus dw. What is zero? Du is zero. So dq is dw, no harm, no problem. State is same. Any state property. du is of course zero, dh is zero, pure isothermal process. Any, whatever it is, same. So this is one comment that I wanted to make last class. I could not get. I could not make it in time. Okay, we are running out of time. So today we made. Second point. Okay, we may call this. Next point is this. What is this? See, interesting. What we found last day. Interesting that this we discussed. That Pv to the power gamma is constant, is valid for. That is you may write P1 V1 power gamma. I think it is better we remove this. Otherwise it will be just for comparison. I drew this. This takes P1 V1 to the power gamma is P2 V2 to the power gamma is valid for reversible adiabatic, not for irreversible adiabatic. Strictly for reversible adiabatic. Strictly, not for irreversible adiabatic. So hence the fallacy, that fallacy was resolved. Beyond this I said. Okay. Now sir, how you know, sir? This is the Pv to the power gamma. Pv to the power gamma. Pv power gamma is constant. Is for reversible. You did a derivation, but why it is? You gave a caption. Giving caption does not mean anything, sir. You can write, anyone can write. So if you can counter argue, sir, this is also equally applicable for irreversible adiabatic. What's the harm, sir? This is the derivation, sir. 10 lines derivation, sir, it is. You counter argue. But you will see yourself that no, that is not true. If you recall the derivation. And this I asked you a number of times and could not finally recall the derivations. First two steps perhaps. First derivation of PV to the power gamma is constant. First two steps, recall the first start, okay, first two steps. dq is du plus w, dq is 0, or what we wrote, du is minus dw. First 2-3 steps, first 2-3 steps only. Du is minus dw, then what we wrote, du is follow. So dq is 0 for what? Nothing to do with reversible and irreversible. So you argue, so yes, sir, dq is 0 for irreversible adiabatic also. Okay, very good, sure. It is not strictly for reversible. So argument holds. Du is minus dw, no problem, sir. Du is what you are writing, sir, n moles, n CBDT. So what's the special about the reversibility here? Du is n CBDT for ideal gas for any process. Any process, sir, n CBDT, reversible or irreversible. So still holds for both of them alike. Then why you wrote what? We wrote what? PdV. We wrote PdV. So what is this, sir? What is this? dW is PdV for reversible. dW reversible is PdV for isothermal and adiabatic, I told you. For irreversible isothermal, for irreversible adiabatic, it is not PdV. If it is expansive, it is less than PdV. It is not. This I said. Also, additionally, I said another thing about constant pressure, constant volume. That I will take up. That is PdV, sir. That does not care, reversible or irreversible. But that is different thing. But we are discussing adiabatic. Reversible, irreversible. dW is strictly for, this is valid. dW is PdV, valid for reversible adiabatic, not for irreversible adiabatic. You have already found that. See here clearly we have seen it is this actually work done is in fact not for irreversible. A further matter, for any reversible, dW is PdV for any reversible on earth, for any reversible. You may note also for any reversible process. Note this, for any reversible. Okay. So we have found. So this derivation is good for reversible. It will be what? It is dW will be undefined. We do not know degree of irreversibility. It can be 0. Irreversible process, it can be 0, sir. What I write, sir? You can write P external dB, doesn't help. You have to write in terms of system parameter. So how you write? So for example, if it is this pressure P2 dB, or if it is a P3 lower, so you will understand. No way. So this was the second point resolved, second point discussed. This is next point. Third point is, so this is so careful. Then question is, sir, is there any equation? Then question is there any equation for irreversible adiabatic? Next question is, so the question remains is there any equation for irreversible? Is there any similar equation? Okay, equation for irreversible adiabatic path? Answer is yes. Yes, there is. What is that? The answer is this. P1, yes, this is P1, V1, irreversible adiabatic equation, path equation, okay, path equation. P1 V1 power gamma times e to the power minus S1, I don't mind, huh? Okay. S1 is, S is what? Entropy. Entropy of state 1. State 1. P1, V1, T1, S1, so on. E1, H1, later on free energy G1. So S1 divided by CV, heat capacity, is what? P2 V2 power gamma e to the power minus S2 by CV. This is the equation. To be deduced, to be derived later on. Later on, after the second law. Yes, after the introduction of entropy. After the introduction of entropy. Second law. So this is, okay. Now, you may note this. Note, okay, okay, this, okay, corollary. Corollary is this. What is the corollary here? You have to be very satisfied. Taking a course, you have to be satisfied. If you are not satisfied, then okay, then it is not worth. So satisfied, I will satisfy you. I am in charge of satisfying you. As if I am representing the subject, so I am taking the responsibility on behalf of the subject to satisfy the students, the learners. Why satisfaction, sir? Corollary, what is satisfaction? For reversible process, second law. According to the second law, later on, which you study, second law is delta S is 0, delta system actually, delta system, let me write. This I said, how to distinguish reversible, perhaps I said, na? Finally, how to single part, reversible or irreversible. When I discussing reversible and irreversible, how will finally the second law. I said, no, how? If you carry out reversible, then it is reversible. Don't have to verify through reversing it. Don't have to. The two now. On, sir, reversible. Yes, reversible. Why, sir? Why reversible? Because it is carried out reversible. This is the answer. But best answer, mathematical, unless it is mathematical, we are not very satisfied. No, we are not giant in mathematics, no, you know. We are very actually strong in mathematics, okay? We love mathematics, okay? To satisfy, okay? So we have to be satisfied mathematically. What is that? The equation. This delta S will be, for the path, delta S will be 0. This I said. Or delta S universe, perhaps I said. Perhaps I said delta S universe. Then delta system is 0 and delta surrounding, in this case, adiabatic, is actually 0. Okay? Delta S okay? For isolated system, I say, for reversible process, delta S universe. For reversible, according to the second law, delta S universe, I said. Delta S universe. But in case of adiabatic, delta S surrounding is okay, 0. Don't worry. So delta system is 0 for reversible adiabatic, right here. Delta S universe. Achha. Achha, let me write this. That is universe. Universe is 0. Then you write, and for this reduces this and this simplifies, and this simplifies to delta system is 0 for adiabatic, for reversible adiabatic. This you understand easily, but don't worry, this is, you will not take up, because this is surrounding is not participating, because surrounding is isolated, insulated, no, so no change in surrounding, delta surrounding. Delta system is 0. Delta system is 0, star, quickly. Delta system here, star here, this is. Delta system is 0. For reversible, what does it mean? System is what? Any change? of the path S2 minus S1 is 0, or S2 is S1. Substitute back into this. Then substitute into this, you get this. So we get this leads to there P1 to the power gamma is P2 reconciled. So we are satisfied. No argument, no murmur, no objection. Okay, happy? Because S2 and S1 cancel out. They cancel out S1. This leads to, leading to what I have followed this. This arrow means leads to, okay? Reconcile. Right here, leads to, I don't have space, leads to, anyway, this is understandable. So, reversible Adiabatic, you are returned to P1 power gamma is P2 P2. P1 power gamma is P2 power gamma for reversible Adiabatic inscribed. Okay, this actually, you must actually keep. So, over this third point is very interesting. Still another point. See, irreversible, free expansion, irreversible Adiabatic. Recall. I completed, na? Free expansion, chatting table also, na? Remember. So recall the free expansion. What are the other names? Yes, you tell me. Okay. Subnil. Will tell us what is the free expansion. Other names of free expansion. Free expansion. Good. Against zero pressure. Against vacuum. Vacuum is actually technical. That is zero pressure. Mathematically zero pressure. Expansion against vacuum. So free expansion. Recall the free expansion. Irreversible Adiabatic. Okay, happy to? Adiabatic process. Takes time though, but quickly tabulate. Recall, irreversible. So DQ, chatting means chatting is what? DQ. What is this? Chatting. DQ is, what I do? DW is then. Okay, this was done quickly do yourself. Du is DH is. Okay, from it quickly, DQ is no, irreversible 0. DW is free expansion, no barrier, no trouble, no effort, effortless expansion. Again, from your mathematical formula, P external dB. What is the external, sir? 0. So we don't have to actually amplify on that. We don't want to integrate nothing, sir. Stop there. Work is stopped. Work has been reduced to 0. So 0. Du is what? As you know, N CBDT. But first law, yes, is NCBDT, right? Is what? For the first law, 0. First law, quickly. DQ is du plus. Every so often you use the first law. Keep handy on the table, on the desk, pocket. Take this, okay? Anytime you actually pull out and say, oh, first law. If you should forget. So frequently you will use here. DH is, this leads to what? This means what? DT 0. DT is 0, okay? Or T is constant. Okay, this I'll say T is constant. This I'll give you. DH is likewise, if T is no change, NCP dt is also likewise 0. Quickly, finish this. As a finite change, Q, W, delta U, delta H. Q is 0, sir, W is 0, first law. This is what? NCB delta T. Delta T means what is this? That is delta T is 0. That is, tell me, T2 is T1. T2 is T1. Final, whatever, T2 prime or T2 name does not matter. You understand, final is initial. And delta H is 0, keep this. This I want to focus, yeah. This point, next point is here. Temperature same. What is the indication? Isothermal. The same behavior as the isothermal. So it is isothermal as well. Adiabatic process, this particular adiabatic process is isothermal as well. So, okay, right? Isothermal property. Isothermal. Oh. I should not. So write this nicely. Remove all this, huh? Remove all this. All. So a pre-expansion irreversible adiabatic process, this particular type of adiabatic pre-expansion, I am writing, adiabatic process is an isothermal process as well. As well. Happy? Recall? What you recall? Anyone can recall? How much you can recall? Similar statement I made. Anyone can give me that statement? You remember? I made a similar statement. This is for understanding. A pre-expansion process. Pre-expansion against vacuum. I discussed. What I said, and then comment I made. And both underlined the comment. What is that? Pre-expansion we discussed where? We have discussed only isothermal. And this is a reverse, this is a adiabatic currently going on. So isothermal, pre-expansion isothermal. That is the maximum degree of irreversibility. Remember that. Pre-expansion also maximum degree of irreversibility. You cannot have greater driving force. Full driving. P1, full, P1 minus 0, full. Any pressure you apply, that will be finite, limited. Cannot be as much as P1 minus 0. But happy? Okay. What is that? Pre-expansion isothermal process. Get back. See what comment you wrote there. What the comment you wrote is just isothermals. Recall a pre-expansion irreversible isothermal process is an what? Yes, what? Good. dq is 0. The outcome is what? d is 0, dh is 0, and since dw is 0, pre-expansion dw is 0. So dq is du plus dw. du is 0 because isothermal. dw is 0 pre-expansion. So dq is 0 like adiabatic. No heat interaction. The thermoset may be there, but it is sitting idle, jobless. Its presence absent does not matter. In that isothermal. So it is an adiabatic as well. Recall. Always adiabatic is an adiabatic process as well. So remember this, okay? Always try to connection. First class, second class, third class, last class. First class and last class connected. Then this is called comprehension. Comprehensive study, for which actually we should, we should achieve, which we should try to achieve. Comprehensive. So over. So this story, with this, adiabatic is over. Adiabatic process discussion is over. Is over. The next what? I'll be very happy if anyone can say, let us say, you can, Somo will be able to. So next what shall I do? Adiabatic discussion is over. This is also thermodynamic question. Easy thermodynamic. Non-thermodynamic. What is next? Oh. What is next? What should I do next? See, don't miss the cue. 1, 2, 3. After 2, 3 comes 3. After 3, 4 comes. I am always verifying whether you are mindful or attentive. You see, take preparation of the previous classes, okay? Of all classes before the current class. Third, 4 typical. What is the topic? Application of the first law for the 4 ideal processes with n moles of ideal gas as the system. So we have covered only 2. 4 ideal processes in bracket I have written. Isothermal, adiabatic, constant pressure, constant volume. So this is the term for constant pressure. So you are so unprepared. See, what else, what I will say? You don't remember that is the second point discussed. Third, constant pressure process. So what we will do now? Next, remove first. This topic is over. Third ideal process is constant pressure. Unless you have a planning, good planning is there. A systematic, sir. Yes, sir. Systematic. Oh, you said what? That you have discussed 4. Suddenly I said, as he says, entropy. You know what is entropy? Suddenly one line, one equation, entropy is over. One equation and entropy is over. The second law, before entropy comes, you have to actually, how the entropy is actually coming into picture. And the Carnot cycle, you know, there is a cycle called Carnot cycle, and that will be this outcome is this. So it should be very systematic, covering everything, okay, covering the points, the relevant points, relevant topics, subtopics, constant pressure process. Process means constant pressure process of expanding or compressing ideal gas. We are considering expansion. So let me draw this quickly. So I am checking. That's why now it is taking time also. I am losing time because but otherwise I am not satisfied. See, you are blindly writing that and does not satisfy me. These I am saying. You are writing the notes. This particular phrase. Note. Have you taken down the notes? So what will you do? Will you taking down? Put it away. Here. Down here. Everything here. PV diagram. Okay. This is the constant pressure process. 1 to 2. Reversible. So I am saying reversible. Reversible first. Reversible first. Reversible. A reversible. So what is the sketch? Is it reversible or irreversible? Your name I forget. Your name I just now forget. You are Ayush. It is reversible. The one I have drawn is reversible or irreversible. The very look. You just see and tell answer. Please. Reversible. They answer promptly. Why? Single arrow. Single arrow. I have not given a single arrow. Double. Oh, double arrow. Dotted line. That is not the answer, not at all. I may not give. 1 to 2, you can see. Journeying from 1 to 2, you don't know which is the direction. Give the arrow, sir. Otherwise, I don't know the direction. I know 1 to 2, but I have 10 minutes. 1 to 2. See how many times I have emphasized this point. In equilibrium state, passing through continuum of equilibrium state, hence it is represented as solid line. As different from dotted line in case of irreversible, because dotted, well, I am not sure, dotty, I am uncertain. Ayush, okay? So it will be, if it is dotted, then it would be irreversible. I am checking all the time, okay, how much you are on guard. 1 to 2. What is this? No, no, don't peep. I don't. Okay, be hidden. Okay, so he's very interested in the class now. Seeing there, okay, what is me? I'm missing perhaps something very important. So I cannot miss. I cannot afford to miss. So from there he's attending the class. But here, no charm. What's the use of this? Okay? They are very interested because others are hearing very seriously, sincerely, attentively, and I'm missing out. No, it cannot. It cannot. So I must actually try to make it as much as possible. Just take a peek into this. All psychological problem. P, since constant pressure, you know, P V1, T1 as it should be, P V2, T2. Happy quickly, nah? There is no time for actually, this thing. But if the process, you have to execute the process, actually. Execute the process. This you recall, this I already told you. So very interesting. So P, state 1, right? Nicely. P, V1, T1, N moles, ideal gas as it should be. Next is what happens? Here actually reversible. How will get from state 1 to state 2? You have to move. The system must move from 1 to 2. How to move? You cannot change here because it is a constant pressure restriction. So you should work from the other side of the surrounding, thermostat side. Thermostat is what? It is actually very interesting. It is not a fixed thermostat. But static thermostat is what? T1. Then it must go to T2. We call this T2. You may note this. V2 greater than V1. It's expansion actually. T2 greater than T1. So T1. So how to get to T2? In a reversible means reversible manner. So T1 plus dt, since increasing, for cooling other way, decreasing, okay, minus dt, okay, but it is follow T1 plus 2 dt and so on until T2 minus dt and then T2, okay. So this is what, this is which approach? Reversible. You know this because, and this is the outcome, this is the process, okay. This, I'll reach here, you reach there, state 2. State 2 is, tell me, P cannot change, V2, T2. So recall this, okay. You cannot change. This is the beauty of this process, or this is the specialty of this process. No pressure change. Outcome this, okay. This part shown here. Reversible. Reversible means, the moment this T1 plus dt, recall that. A little bit change, infinitesimal small change to dV, V1 plus dV, then V1 plus 2 dV. Volume is final volume. Okay, so start. Reversible. So small du quickly and very quickly. dq is what? You don't know. Which you know, which you best know. Easiest is dw may be easy. Which is the, thank you. Okay. dw may be easy. Why easy? dw for 2 reasons. dw is pdv. For reversible it is pdv. Again, for constant pressure reversible or irreversible. For constant pressure reversible or irreversible pdv. So don't worry. pdv. Leave it there. Achha, du is what, by the way? Du always, as I told you, don't mind, is for any process. It should be NCBDT for constant volume process for other systems. Remember, like non-ideal system, like real gas, liquid, solid. But here no problem. dH is obviously NCPDT. And you remember that dq is what? You tell me. dq is what? dq is what? First law always. Good. dq is du plus dw. Okay. dq is du plus dw is, recall that. dw is pdv is d, p is a constant, u plus pb is dh. Recall that. I told you under constant pressure dq is dh. Under constant pressure. Is it? PdB, dPb, PdB becomes dPb because constant pressure, otherwise it will not be. So, come in, okay. dq is dH. This I said. There is another condition. Actually, you know what is that? You may say, you may note that. What's the other condition that we not come across often? No non-mechanical work. No. But this is here. There is no scope of non-mechanical work. So okay. So dq is dH means ncp dt. So you may check PdB is what? What is dW should be what? Should be, take a look. PdB is what? PdB is what? Tell me. PdB is what? PdB, note, PdB plus VdP, PV is RT. PdB plus VdP is nR dt. What is the VdP is how much? In this case, constant pressure out, or PdB is what? Tell me. nR dt. You can write nR dt. You may check in a different route. That is cost check. Very satisfying, very convincing. Fine, sir. No, not this way. Alternatively, what you will do? Tell me, suggest. dW I want to know. So what shall I do? I don't take this approach. This is satisfying. The answer is over. nR dt. So dW is, tell me, sir, first law, sir. What is dq, sir? dq, as you know, ncp dt. You know, this is a basic definition of dq and heat capacity, Cp. This is ncp dt. From this I said though, but you know what is the definition of Cp? dq dt at constant pressure. So dq is ncp dt, it doesn't require any restriction or any condition. This is the very definition, heat capacity. Cp, dq dt at constant pressure, and since the pressure is constant, so Cp, dq is ncp. Anyway, also from here, the number of ways. So what is this? dq is how much? ncp dt. Minus du is ncb dt. So ncp minus cb dt is Cp minus Cb must be R. Okay, if it is molar, if it is for 1 mole, this is what type of heat capacity? I tell you, warning. This is a molar heat capacity, means 1 mole. If it is not molar, it is n mole, then capital Cp. Then what would be this? Cp minus Cb would be okay. Itself is this multiply Cp minus Cb is nR. Okay. So if you multiply, this will be capital. But don't worry, n Cp minus Cb is R dt. So reconciled, same result. Alternative, same result. So you are very satisfied that anyhow do, no problem at all. Okay. Happy? Over. This is over. You know. Next, what shall I do? Next, you are more mindful. They are outside. Now he's sticking his head onto the table. It is better you try to learn from them there. You learn more. Because you always think that you are missing. Here you say, nothing to miss here. What's the use of this class? This is very important. Happy? Okay, so next what shall I do? Guess, what shall I do? Next, this is the dq. Next is the, can I remove this? Alongside may be better. I'm removing this. Okay. So number of thermostat. Okay. An infinite number of thermostat to be used. This you should note that. Unlike in isothermal, how many thermostat you use? In isothermal process, you have thermostat, which is surrounding actually. How many? I discussed isothermal is over. It will not come back. Only you have to face in the examination some questions. How many thermostat in the isothermal process? Isothermal is also thermostated. Is thermostated, must be thermostated. Two no. Initial state to final state, but thermostat is 1. That is constant temperature. It cannot. It is T. Isothermal process is T. P1, B1 to T, P2, V2. So there is no scope of two thermostats. Okay. So careful. Okay, happy? So I always check. Check actually if you are okay. So what is this? Where you are? Start. Integrated from quickly and very quickly. Q is, W is, delta U is, delta H is, you don't mind, NCP dt integration though. You note, every point you should note, what is this? Integration from 1 to 2. N can be taken outside to naki. A CP, CP is a function or CP is a constant. 3 by 2 or 5 by 2 etc. 5 by 2 5 by 2 for monatomic at least. Okay, or diatomic also 7 by 2 good, very good. Very good, very good, 7 and 9 by 2. Okay, so what is NCP outside? NCP, write this nicely. NCP T2 minus NCP. Thank you very much. Thank you. Very good, very good. Okay, always please do this. I'll be very happy rather than I will be annoyed. Okay, happy? Delta H. Similarly, delta H equally 1 to 2 is NCP T2 minus T1. Careful, careful. Q is what? Q is delta H, you know, the same result as here. Here you see integration. NCP. Results is important here. T2 minus T1. W is what, sir? P into P2 minus, good. PdV into, right, do that. Let us do this. 1 to 2, 1 to 2. I use P can be taken outside. Can P be taken outside?
Yes, sir.
Good. Constant pressure, sir. Of course you do. By all means you do, sir. Is P into V2 minus V1. Of course, if you try, it will be NR times T2 minus T1 as good. I have a number of relations connecting, interconnecting. Over. This is okay, happy. So this is reversible. So one thing I tell you, I will soon after this over, I will show you why du. I will explanation little later. Although it is a constant volume, note du is Cv dt. The relation. Note the relation. Du is and Cv dt. Should hold good for a constant volume process. In principle. But it is a constant pressure process. So why are you? Constant volume process. The definition, if you follow the definition, Cv, you know, definition is what? Okay, constant volume process. Recall. What is called constant volume process. But we are using it here. Using the relation for constant pressure process also. For a constant pressure process. Actually, for ideal gas as system, for all systems, okay, for constant volume process, for any system, with any system. But for ideal gas as system, the relation applicable for any process is applicable for any process. Is universally applicable. Is applicable to any process. Not necessarily a constant volume process. A constant volume process. Okay, careful, huh? To be shown later. To be shown. To be shown soon. To be shown soon. To be shown soon. Okay, it's over. Oh, irreversible. Next is irreversible. So can you please tell me? It's okay. What I said, wanted to tell, du is NCVDT. Du is NCVDT. In principle, why? Why in principle? Tell me. Recall here. If you must recall, okay. Recall here from this. Recall. Okay. I mean, too many single star. Okay. Double star. Recall. Definition. CP. Okay. CV is what? Tell me. Del Q, del T. If it is 1 mole, then size is 1 mole of the system, of the iron. 1 mole required to raise the temperature 1 degree. Okay? Then that is heat capacity. Heat required to raise the temperature of a body through unit degree. So see, since it is constant volume, this must be constant volume. Happy? Okay? See. Acha. At this stage, can I remove this? This. Very good. This. Okay? Note, explanation. CV, recall. So all recall. Then see what is DUDT? dq at constant volume, first law. dq is du plus dw. Since constant volume, no pdv, no dw. So dq is as good as du. Recall is du dt at constant volume, from which you get du is cv dt. For 1 mole, so it is 1 mole, and for n moles, Somo, this often ask you, for what type of system, from here to here, what type of system? Constant process, system. Constant volume is the term process. What system is your liquid, water, gas, real gas, ideal gas, solid, what? Huh? General. Why have we made any restriction? First law has not made any restriction, that is solid or liquid. Follow? This is the basic definition of heat capacity you read high school. Or it is, okay, in differential format. Heat required to raise the temperature of a body of given size. So this means this first law. You may write this. Recall this from first law. dq is du plus dw for constant volume is 0. Okay, happy though? Is okay? I am removing all this. Okay? All, remove all these things. All. So I have made a problem myself, and I will solve this with you. This is pending. Okay. Good boys are very good boy. Okay. Good. Very good. What else? It is all you are. All remove. Remove. A reversible. B will be what? Oh, sorry. This I removed. I am very sorry. I should have not. This actually same. Now here, irreversible. How the process will be executed? Two thermostat. Right answer. So yeah, I told you. So you start from again. I am showing here. T1. Then say abruptly. It can be number of steps, but better is the final step. Temperature T1 to T2. What is the root again? Reversible. This is. What is the? If you do this, you will start from this to this. See again. You see. Initial state. It will go to the final state. Same final state. How will you show this? How will you show this? Here. Now you be careful. I use. How shall I show? It starts from 1 and ends to. It will end because see P no problems are final T2 final temperature is T2 no problems are T2 P T2 and V2 automatically so final state same. So how superimpose with dotted line. Why irreversible? Dotted so right here This is for reversible path, irreversible. Reversible constant pressure, irreversible. So good, very good. This okay. Reversible constant pressure, irreversible constant pressure. Happy? Happy? Okay. Superimposed. Work done is same. What is this? I wanted to tell you here something. Okay, very good, very good, very good. So final state same again. Oh, this path has not affected the final state. Has not. Is not affected. Isothermal also is shown. Same. I showed that in isothermal is not affected. Constant pressure is not affected. Constant volume likewise will not be affected. Who will be affected? In which case it will be affected?
Irreversible.
Adiabatic actually. Path. Since you are saying path dependent means you don't mention irreversible. Means reversible to irreversible or one irreversible to another. So you don't have to. Adiabatic process is here path affects the final state. So special, exceptional. And accordingly you should be exceptionally careful when you are taking up adiabatic for your study. So if it is same, then it is very interesting. Do quickly and very quickly. dq, dw, du, dh, from which the same result, same result as, that is very important point. Same result as, tell me, as reversible, sir. As reversible, constant pressure, constant P process. Same result. Why? dw is what? Work done is different. Work done, who has touched this? Here to here, both cases. Is the load changing? The load is greater or less? Area under the curve, another way. Fillings, area under the curve, both cases same. Fillings, graphically, analytically, conceptually. So dw is PdV. Oh, sorry, what is this? Work done is same. And as I told you, this is the reason why dw is PdV. See, follow. See, note, careful. Although irreversible, since the process is constant pressure, constant pressure 1, dw is always PdV, See, reason answer, no problem, same work. Note this, and this will similarly in case of constant volume. Okay, that's why I told you now that reversible work is not greater than irreversible work, not different from irreversible, is not greater than, as often we hear reversible is maximum work, but it's the same work because that is actually directed to isothermal and adiabatic, and they are very important processes. And they are used in the Carnot cycle. So that's why that is so popular that it is masked other possibilities. Totally masked. Students don't know actually that reversible may be same as, reversible work may be equal to the irreversible work in certain situations. And coming constant volume. Careful. So gentlemen, du is what? NCP/dt, write this. dq is, tell me dq is du, dh is NCP/dt, all same. No harm. Okay, do this same way. PdV is nRdt, etc. Write that. So what will get? So I have to remove this. Because I have to make room. But it will be good if I place alongside. Q is delta H. While you read this, I remove this. Q is, W is, how much? Same, quickly jot down, same result. W is what? Q is what? NCP, T2 minus T1, P V2 into V minus V1 is NR T2 minus T1, all same. Once more you write rather, NCB, quickly, though unnecessary exercise, but because I have already declared, we have already declared that same result. But still I showed you, okay? I'm removing. So with this what we have done? Completed. Completed what? Next will be what? Constant volume. So let us start fourth one. Okay, before this one job is on hand. What is that? A moment ago I committed that I will show that du is LCVDT for constant pressure process if it is an ideal gas system. This also. Next. Then I will take up the fourth one, constant volume. Okay. Just quickly, you follow me. This is interesting. In the assignment, I have given one similar problem. Last problem may be possibly. Last problem. 1, 2, 3, 4, 5, fifth problem. To the actual assignment that I remember. But unless these are clear, you cannot solve. That's why I didn't. Okay. Maybe if time permits, and then I will take up one problem for discussion and other things. Okay. But in case after. I know. Today is the assignment date. I know that. Many students perhaps have not come today because of the assignment problem, maybe. Okay, so but when they will repent, maybe. Okay, I don't know whether they have to repent being absent, but so follow me. Okay, but this happens. Okay? Last day I thought actually that I will clarify this constant pressure, constant volume for total constant. No, constant pressure remove over, but. Achha, no. To show that job. Next, to show that du is NCVDT for a constant pressure process. The relation holds good even for a constant pressure process. Even for a constant pressure process if the Shohok is not cooperating. Good. Constant pressure process if the system is, tell me, the system is what? Du is NCVDT should be even constant, should be applicable for constant volume. A moment ago I said constant pressure process if the system is what? Ideal gas. So what you will do? Go back home and see conditions what are written, okay, from first day till today. So this is for a reversible, or this is reversible PdV, P external dV, and then it is okay. This is better, that is less, okay, fine. Then this is again say state function, this is path function, okay, but this is equals to this. The extensive property, intensive property. This is the first law, okay. And then this actually for reversible how it is working. So reversible, irreversible state, path, constant pressure, constant volume, adiabatic, isothermal. With adiabatic added complexity. Who will care? Who will manage? You. Put in effort. Otherwise, no. Okay. So ideal gas. Okay. See, this is the logic. Logic is this. Follow me. Very easy. PV diagram. This is a constant pressure process I am considering. 1 to 2. 1 to 2. Question du is. I am writing du. Du is what? You wonder. Du. Constant volume we know, sir. Du is NCVDT. Du is NCVDT for constant volume process. Always for all system. No, for all system. Du is. This I say. Okay, 1 to 2. So this is the question. Under constant pressure, you don't know. So what you do? So you give us assign P1, V1, T1. Assign the state. P2 is what? This is what? Tell me. P1 goes there. Constant pressure. P1, V2 has increased. T2, and then you do another thing. Yeah. Sorry. straight up, straight up. So this is what? 1, 2, 3. You are moving. What? Under what? Constant volume. Constant volume. So what do you write? This must be which pressure? P2. Volume has been V3, you might say, V3, V1, V1, I'm very sorry, and temperature must be T3, I'm sorry, T3, happy? Next is, let's consider, I've done to what extent? Here, 1 to 2, what extent? So that volume becomes 10 times initial. So let us consider V2 by V1. I consider a value. What is this? 10. 10 is V2 by V1, 10 times. But this must be equals to from 1 to 2. From 1 to 2. 10 is V2 by V1, then what it is? Then constant pressure. Constant means T2 by T1 is what? 10 as well. I'm telling them I'll do something 5 times, 7 times, 8 times, see opposite 10 times. Sir, you have certain, sir, your interest and say your deceitful planning, sir, some advantages, that's why you consider it. No, you consider it in 3.3. I don't right, 3.3. Knocking. Then I do here also, similarly, I go to what? V2 is 10 times V1. Then this is 10 times. Pressure is how much? 10 times again. It's same. So what is that? And what is that? 1, 2, 3. I consider I don't change for some reason. To demonstrate this, I don't. I consider 3.3. Then you will see something. 10 is what? Tell me. P2 by P1 is what? T3 by T1. What does it mean? See? What does it mean? T2 by T1 is T3 by T1. Then what is this? What does it mean? Or that is or is what? T2 is T3. Just I planned this way. T2 is T3. T2 is T3. That means this temperature is same. That means this can be connected with an isothermal. Oh. Isothermal, right? This is constant, right here, constant pressure. Right, somewhere. Okay, don't be clumsy. This is constant pressure. Constant P path. This is constant V path. And right, this is what? Constant isothermal path. Constant T path. Now you follow me. So I give you actual singular, I'm reaching 1 to 2. Can I remove this part, this side? Now. So you'll get the answer now. I'm considering 1 to 2, du 1 to 2 is du 1 to 3 plus du 3 to 2. Do you have any objection? Your name is what? Your name? Nobonita. Audrey, Audrey, difficult. It's okay. 1 to 2 is 1 to 3 plus 3 to 2. I've written something. Du 1 to 2 is du 1 to 3 plus du 3 to 2. First of all, why temperature we are considering? This is a state property. What's the problem? This is assignment number 1. Assignment number 1 discussed. Anyhow you get 1 to 2. This change delta U is whether this way or that way does not matter. So what temperature you are thinking? Temperature will come later, but you answer this first. This is always true, okay? Because it is state property. Du is state property. U is a state property. Is a state function. Happy to? Achha, since I'm going this way, this is the original problem. So I give double arrow in the other two. Alternative. 1 to 3, 3 to 2. So time actually I am trying to avoid this constant pressure. For du, constant volume should be the requirement. So it is better I take up this. So this is, now what is this value? Remove this. What is this value? D1 to 3, tell me. D1 to 3, how much? This is a constant volume process for any system. Doesn't have to be ideal gas. For any system it is what? And du 3 to 2, 3 and 2 is what process? Also what is the du? For ideal gas, isothermal, what is the du? 0, because U is what? U is a function of temperature alone, and that temperature is a constant. Like U is 3 by 2 at T, function of temperature alone, and if T is a constant, then du is 0. So du is so this is the discussion. So you should be convinced forever. Forever that for ideal gas I don't care. You have to say I don't care with emphasis, conviction that for ideal gas du is forever infinity. I will not look at the path. It is ideal gas. If it is non-ideal, then tell me, let us see. Tell me, if it is non-ideal, then what you will say? So non-ideal system, non-ideal gas, liquid, solid, what you will consider? I want to actually, okay, to answer this yourself. It is always forever du is instability, but in non-ideal system, what you will comment? Or du. 1 to 2, you don't have to write, du is instability. This is always, for ideal gas, always. By the constant pressure, valid. For always, for any process. But for non-ideal system, what will be your comment? I am discussing this today, not in that earlier. Just today I am asking someone and you could not follow. What the comment you will make? The du is instability for constant volume processor. Is it difficult? Is it difficult? Use instability for constant volume processor for any other system. It must have to be. It has to be constant volume, otherwise it is not valid. Okay, but for ideal gas is an exception. This we try to understand. So why it is always true? This I showed you a moment ago. Cb, from the scratch I started. Cb is del Q del T at constant volume, from which you get del U del T at constant volume, from which you get du is CBDT for 1 mole NCBDT. So that I also asked someone that which system it is. I asked him, which one? He said constant volume. No, constant volume is a process. The system. I don't know, maybe later. Ideal gas. So any system. General. So du is NCBDT under constant volume. Okay. Any system, sir. Constant volume, no problem. Du is NCBDT must be. So to be constant, then that is a requirement. Constant volume. But for ideal gas is free. Ideal gas is free because of this factor. Ideal gas internal energy is a function of temperature alone. Means this term drops off. Internal energy is a function of temperature alone. This will not be zero in case of real system. For real gas, this is non-zero. In isothermal expansion, constant temperature, but expansion means internal energy has increased because there is attraction. Potential energy increases, there is attraction. Against the attraction, there is expansion. So internal energy means potential form of internal energy has increased. So internal energy, though constant temperature for a real gas, for example, internal energy change is not zero. If it is not zero, this does not hold good. It is non-zero. Can it be same? Enough preparation. Otherwise, no, you will actually fumble here. You will be embarrassed, humiliated. No. Preparation. You are actually already, there are backlogs, I hope. Okay. Don't think this is actually a ready-made question. Will be asked. Oh, prove that. Can you prove P to gamma is constant? Don't expect. Don't prepare for this. I'm telling you even that, don't prepare for that. P to gamma is constant. You'll do, but you don't expect that question ever. ever. Maybe there will be someone else there, maybe that teacher may be someone else. But this teacher will never ask to prove that Pv to the power gamma is constant. Be careful. See the okay, assignment problems. Over. Happy to? Can I remove all this? What remains? And then ask back. Then in the class we have some queries. Not before the day before the class test. Before. Okay? Okay, much before. Okay? Long before that test day. You are preparing, sir, you are there. This I understand, sir, but this is clashing with you what you said before. What are you mean? Books? You like books? Over me, this book is saying this, sir, but you are saying this. Okay, argument. Welcome. Welcome. Don't sit idly, okay? Don't think at the day of examination CP. What should I say? You should know to actually know what happened actually previously. How many students performing, okay? What remains? What remains? Third over. What? Constant volume. Quickly, finish this. Constant volume. Good boy, good boy. Quickly. Why it is taking time, so much time? Because you cannot answer. You cannot answer, so I am not satisfied. I'm not pleased. I cannot move on. Keeping you in the dark, what's the use of my actually completing the course, taking the class? You are in the dark. At least one or two or few more should answer. Constant volume process quickly. Again. Start. Again, if we must. Oh, quickly. Sorry, very sorry. Quickly, very fast. This will be since this we have discussed so much. Others quickly. Constant volume should be vertical one, na? Vertical. Also, let me draw this way better. This is your 1. This is your 2. How will assign this? State 1. State 1 is PBT. In terms of PBT, okay. P1 V T1, P2 V T2. For what process I have drawn this? Reversible, sir. Okay. Solid line, sir. Solid. Constant volume irreversible possible. Don't think this, okay? It is actually equilibrium through passing through reversibly carried out. Quickly, how to execute? Again, do this, although there is no point discussing this, but for your satisfaction, I am doing everything. So, no doubts may remain. No, follow this. Oh, I am very sorry. This is a constant volume. Volume cannot change anymore. Volume cannot change. It is a closed box. So what is the state 1? Tell me. Write here nicely. Tell me that one you write. P1 N moles. N moles system. Ideal gas. Very good. Similar to constant pressure. Don't worry. Similar. Exactly similar. So what shall I write? Tell me. P1 V, which is not changing this time. So how will process be executed? So start. Bank upon the thermostat. Like before. What is the initial thermostat? Tell me. Thermostat, okay? Reversible. T1, start T1. What will gain here? No volume change. So don't expect there is expansion. What will happen? Temperature will rise, pressure will mount inside. As I said, constant pressure and constant volume are mutual alternatives. Either these or that. Isothermal, adiabatic also. Either isothermal or adiabatic. Read all these things, interesting things, okay? Ideal gas. T1. Happy? So T1 it goes to T2. So how is the large number of means infinite number of thermostat. T1 plus, since temperature is increasing, you consider T1 plus dt. Yes, same. Don't worry. T2 minus dt to final T2, right in bracket the reversible approach, sir. Reversible approach. Okay, over. Okay, this is approach. And what is the state 2? While also state 2 here itself. There. I have to show. The volume, through volume is so, but your volume unchanged. So inside pressure has mounted, inside temperature has increased. So that's it. So what is the quickly and very quickly. This is so easy. dq, du, dw, du, dh. dq quickly. Which is easiest? Du, very good, very good. At least you are participating. So du is what? So always forever, forever NCP. See, ideal gas. dH is what? Forever. NCP dTs are irrespective. dq is what? dq is what? Under constant volume, dq is du. Under constant volume, dq is du. Remember, what was dq is equal to what? In constant pressure, dq is equal to what? dH. dq is equal to dH. In constant volume, dq is equal to du. There is a notion false or erroneous that dq is dH. Enthalpy, enthalpy means heat interaction, enthalpy. No, it cases heat interaction is equals to internal energy, change in internal energy, related to internal energy rather than enthalpy. So this is the example. So dq is du. First dq is du is what? Here also get du plus dw. So NCP dt. Also you write it, dq is du is NCP dt. Good. Okay. dq is du. So dq is du and constant pressure dq is dH. Okay. Careful. So all finites NCB T2 minus T1. All finites W is 0. Delta U is NCB T2 minus T1. Delta H is NCP T2 minus T1. Moreover, I don't mind, I tell you, okay, this is informal, but I don't mind if you take these notes in the test, exam hall. I don't mind at all. Our books also. Books, all books that I have referred, or you do have any other select books, all, carry them. Unpicked, go to the, answer my questions. Even this note, class note, all you may take. But normally I cannot do this because there is some, this is not practice here. So the other teachers and other invigilators may not take it actually very well in the semester particularly. And class test sometimes I do. I've taken. But this is different discussion. I don't want to discuss this, but I don't remember this is the principle. That you can take all of this, all that scale, then I don't mind at all. I will encourage, sit down please. Then what will happen? I say, no one is looking at this. In the question, no one is looking at it. They don't know what to do and what to do. This has happened. Remember, this will happen. If you go this way, this will happen. And you will go score blank. Happy? Very happy. 1 to 2. Okay, so now irreversible. This constant volume, this is reversible. Oh, sorry. I'm very sorry. This is reversible. Reversible constant volume. B is what? B irreversible. Okay. Irreversible also. This is okay. Irreversible. How to carry out? Tell me. Yeah. Show me. How shall I carry out? T1 abruptly to T2. Same. Okay. Here you write an infinite number of thermostats. As before, infinite number of thermostats. In case of reversible, constant volume, in case of reversible process. Happy? Okay, over. So how will you sketch this here? I will show this dotted line. So yellow chalk may be helpful because you can at least distinguish this. You can see final state is final state. Path has not affected the state. You are all convinced. Cannot change. Okay. So good. Over. So now irreversible you write yourself. Next remove this. Irreversible. Tell me. B. Irreversible. Right here. Quickly. Very quickly. Irreversible. dq which will change? First of all, dw will change. 0. du is forever. dq is forever. Okay? Hello, your name is you. I know your name. Vidyut. See, will anything change? See, dw reversible does not matter. No volume change. Out. These are forever true for ideal gas. And then first law or etc. All unchanged. So all All items unchanged. Unchanged from unchanged. All are unchanged. Remain unchanged or unchanged. In comparison to the reversible. The reversible results. So I don't do anything. But this side is also same. Okay, over with this. So summary will help you. Quick, small summary may help you. Just here. So you will enjoy. Means summary means at the end what you have started. If you take a quick view, summary so far. Don't worry. This is very synopsis. Start. Right. First law you write always. dq is du plus dw. The first law. First law. Oh, good chalk is necessary for all these things. Okay, good chalk. What is good chalk? Start summary. 1. Isothermal. First is 4. Isothermal. Isothermal process. Isothermal. What is the isothermal means? du is 0. Constant du is 0. So what you get? So du is 0. So dq is dw. These are the salient features of isothermal. Another thing is what you write: temperature unchanged, T unchanged, both P and V change. Both P and V change. Like tell me P1 V1 to P2 V2. T does not change. This is the okay. Hey, what are you doing there? Repairing watch. You what is your name? Huh? Somodip. Oh, okay. What are you doing? Oh, writing. Okay. Second, adiabatic. Quickly. Adiabatic. Adiabatic. Sorry. Adiabatic. What is what? Relaxing. Almost is relaxing. He is smiling and amusing. Very interesting. Okay. See. And dq is. See. Take seriously. dq is 0. Okay. That means du is minus dw. You may write or may not write. dq is 0. You may write. This is good enough. This is good enough. Okay. So who changes? Let us see. Let us see how much fun it is there. I wrote T unchanged, both P and V change. You have to say what will happen here. What shall we write in that place? Isothermal, I said T unchanged, both P and V change. What is your outlook about adiabatic? See, sitting. That's why I said don't make fun. Don't think amusing. Life is very difficult. A moment you don't know when you'll be slipped. Okay? So all 3 changes. All 3 PVT. Yes, very interesting. Here all 3 change. T1 V1 T1 to P2 V2 T2. All 3 change. P V T change. Take a look there. Third is what? Constant pressure. Okay, constant pressure. What is this? What is there? What is specialty? What is specialty? I don't know. What is specialty? Yes, one specialty is there. Of course, constant pressure. dq is dh. You may note this, no? This is specialty. Constant pressure dq and dh same. Then what is what? You can tell me. Tell me who will change? How many will change or not change? All 3 will change or unchanged? All unchanged.
P unchanged,
P unchanged, right? P unchanged. Both T and V change. Okay. Fourth, constant volume. Happy? Yes, let us see. Your name is Anurag. Anurag, what's the right? Constant volume?
Delta Q equals to delta U.
U. dq is du. This I did not. I don't say delta. Delta is delta. This is delta. Remember, I use at least. It is del. Del y, del x. State function. This is d I said, but this is twisted d. Path function d. So dq is speciality is what? Du. Okay. dq is du. No, that is fine. So b unchanged. Very good. Both P and T change. Very good. At least we have finished satisfactorily that topic. What was the topic? Application of the first law to the 4 ideal processes with n moles of ideal gas as system. Okay. Over. Next is just one point is yes, next. All this, all over. Don't have to, but you prepare yourself seriously, all serious. So the assignment actually is deferred next class. Perhaps I cannot. Maybe after this, after let us see how fast I can complete. I cannot complete anything very fast. Okay, it takes a lot of time. Cp minus relation, the expression for Cp minus Cv. This is very, heat capacity is very important issue, and the expression for Cp minus Cv. Let us see how much you remember. I gave an expression, nice expression for Cp minus Cv. Can anyone remember? General. That is for ideal gas. General I gave. By he is actually not taking preparing himself. Going back home. Going back home sometimes is nil. If you are very smart, then you can prepare yourself here. But I don't see that. So neither there, neither nor here. What will happen? Okay, quickly. Cp, start. Cp minus Cv. Okay, molar. So work is molar. Is del Q starting. Basic definition you cannot avoid. You cannot. Del Q del T at constant pressure minus del Q del T at constant volume. Happy to. Alternatively, help me. Tell me what it is. What it is? Del Q del T. Del Q is what? What alternatively? Constant pressure. Del Q is dH. dH by dt. This I said. Since constant pressure, anybody, any system, solid, liquid, gas, ideal gas included, dH by dt at constant pressure minus. General, right? The expression, general expression, right? This better. General expression for Cp minus Cv. Okay, what is this? Del U. What is this? Del Q under constant volume is du. So it is del U del T. Next is H is what? Knowing with this, H is U plus PP. So do this. Noting. H is U plus PP. I am writing du dt at constant pressure. H is U plus PP plus P del V del T at constant pressure. Do you mind? First term. Do you mind? He has slept. He's down. Oh, that's why he thought that this is a colder place than that. P del V del T at constant pressure is happy though. This part H is U plus PV. U first term, say PV. PV what is a constant? P is a constant. So P del V del T. Okay. Is what? Minus del U del T at constant volume. At this stage I consider something. Now we consider what? Now Cp minus Cv. Cp minus Cv. Keep it, restore it. Equation 1. Leave it. Now I am writing. I am removing this side. It is okay though. Happy though? Quickly. You see now, start from this, huh? Start now. Oh, this side is, now U is a function of temperature, volume. Take a look. Function of independent variable, dependent variable, TV. Any two, remember all those things, given size, molar, 1 mole system. So TV, any two will do, because actually initial state function. State is a function of 2 when given size. So go back. So 2 have written. And what I said, must I consider TV? Any two. Or TP? So it is your job, you consider TP. That I'll ask you at the end. TP. I will show you with TP you will get the same result. Or for that matter, VP. Any. This is the place for independent variable. Method of choice. This is internal energy function of, okay? State is a function of 2. And a state function is also. Go back. No, keep on. We have seen already, noted that, okay? U is, or du is total differential, du is del u, del t at constant volume. You know how to get this total differential in terms of partials, plus del u, del v at constant temperature, dv, okay? Now at this stage you have to consider one thing. At this stage, consider the process is, this is carried out in a constant pressure process. These changes, du, del t, del v, all are under a constant pressure. I have not mentioned anything here. The pressure process is constant pressure. Because CPCB deals with constant pressure and constant volume. And constant pressure has some additional terms. That is the reason. Constant volume don't have such terms. I will explain later at the end. So constant pressure. So considering the process, concerning a constant pressure process, since Cp is a constant pressure heat capacity, constant pressure process, what you write here, follow me. I am writing, or follow me, constant pressure I am writing. Changes under constant pressure. Del u, del t at constant volume. The dt change is affected in a constant pressure manner. Constant pressure. So, constant pressure process, okay? Constant dTp plus del u, del v at constant temperature, dv under constant pressure. So, constant pressure process. Or you say this is a change. Per unit rise in temperature, how much? For what is the change here? For dt. dv is there. I am considering temperature. For dt change, this is du change. Follow this. First is this line. Second is constant pressure imposed. Then I am trying to get unitary method. This change for dt change, when there is change in temperature of dt for 1 degree change. 1 degree change, unitary method. You divide by dt. For dt change, du change. For 1 degree, why I am 1 degree? The heat capacity definition requires 1 degree. Heat is required to raise the temperature of a body to 1 degree. 1. So that's why 1 degree. So I divide by dt. Okay. So for unit rising, so right. So for unit rising temperature, unit rising temperature means dt is 1, okay? So what is this? You divide for dt, so unitary method, or del u, you divide by dt means when is the division with a restriction, it should be partial. It will be converted into partial. See, just dividing, this is pure division, unitary method. So for dt, this much, so is what you get. Write this nicely, very nicely, quickly and very quickly, happy, plus del u, del V at constant temperature. This is for unit rise. Del V, del T at constant pressure. Happy? Okay. So call it equation 2. 1, 2. Okay. This is 2. From 1 and 2 quickly. From 1 and 2. So what you get it? For unit rise interval. So this is okay. This is to substitute this into this. From 1 and 2 I am writing. Top CB minus CB. Okay, from this. From 1 and 2 right. From now. From 1 and 2. Quickly. What is CB minus CB? I am writing with you. Please follow me. Del U del T at constant pressure. This term is this much. So many terms. So write that. For first term is del U del T at constant volume plus del U del V at constant temperature plus times del V del T at constant pressure. Okay. Okay. This term so far plus P copy del V del T at constant pressure minus del U del T at constant volume. Is okay? Any harm? Very easy. Then what you do? This cancelling out, remove this line, remove this line, remove this line over, all over. Continue. So what you are getting finally? You are getting this. So you take del V del T, P plus I am writing, del U del V at constant temperature. These are multiplied by del V del T at constant pressure. CB minus CB is. This is the basic relation. CB minus CB. But we will simplify further. You see, now what is this? Explain. First term. Explain. Explanation. First term is what? Follow me. P delta V del T at constant. First term. First term. Try to understand. What is this? Work term. Work done. Work interaction factor. P dV by dt. Work done. But unit rising temperature by dt. Work done why? Follow the logic. What is the difference between heat capacity at constant pressure and constant volume? Follow the process. Follow the process. Follow the process. One is this constant pressure Cp is rising. Is it 1 to 2? What is the constant volume? Constant volume is what I am showing you. Constant volume C follow 1. This is sorry. This is 1 and this is 2 itself. So no rise. Sorry. No volume change. So what is the difference here? In constant, this is constant pressure heating. This is constant volume heating. What is the difference? You tell me. In constant pressure, you see work, volume change, work is done, extra, no work. So it must be greater. Heat requirement. Who gives the work? Who supplies the energy corresponding to the work? The first law, dq. dq is follow this. dq is feeding du plus dw. So when there is an extra work, extra heat is required. Hence the heat capacity is greater. For extra work, extra heat in case of constant pressure Cp. So Cp minus Cb will obviously contain a term. Cp is greater than Cb, and by this factor, term by term, PdV, work factor. By dt, but unit definition requires for 1 degree rise in temperature, heat required. Heat requirement, heat. Why heat? Sir, internal. Sir, work is can be obtained supplied by the heat. Heat, that means for to perform the work, heat must be supplied by the corresponding amount. By that means greater amount than constant volume. Where there is no work. 1. Then second is what? Second factor is what? This is the work. External work. Done by the system in case of constant pressure process. In case of constant pressure process, P process. You clearly see the figure? Volume changes? Okay, one term. For second term, del U, second term. Del U del V at constant temperature times del V del T at constant pressure. This I will tell you, this is actually internal energy rise per unit. So dV if you don't for the increase, the effect is the constant pressure process. For the external work done by the system in case of constant pressure process, right? For unit rising temperature, of course, for unit rising temperature, otherwise definition. Rising temperature as required in the definition, as required in the definition. Go by the definition and the first law. Two things follow. Two things you follow. That is the definition of Cp and Cv and the first law. First law says extra, in this case, extra, right? Extra work, extra internal energy factor. So what is the second term? Internal energy change. Internal energy change. What's the internal energy change? Internal energy change. Expansion. Which type of internal energy? Sir, when there is expansion against the intermolecular attraction, real system have attraction between molecules, so overcome. When there is expansion, there is attraction, overcome. So this is not what? This is internal energy. This is external what? It is external work against this load, sum of what? And corresponding heat will be required. More. If it is greater. If it is zero, then this also not required anyway. So external part. Internal energy. Which type of internal energy? Internal energy means two types of internal energy. What I said? Internal kinetic, internal potential. Internal kinetic is what? Translational and rotational vibration. Internal potential is what? Positional. If there is attraction, there is a question of any potential energy. For example, in ideal gas, there is no potential because no attraction. So how will you overcome? If they are separated, it does not matter. But attraction, difficult. Means it requires input. Okay. So this is the internal energy increase. Energy in the form of potential energy. Right here, because of intermolecular attraction, right? Because of intermolecular attraction. Intermolecular attraction. A force. In the form of because of intermolecular attraction, etc. Right? Internal energy increase. The work done, internal energy increase. Why increase? For volume, you know that there is attraction. So if you separate them, internal energy is increasing. Position, like this position, because they are trying to come close, and you are separating them. If there is repulsion, they are trying to separate away. Bringing close is again increasing, again opposite trend. They are tending to come close, so separate them is energy is more, potential energy. This tends to be where? Here, or maybe ground. Here. So here, against that, potential energy is increasing. So so from here to here, no potential energy decreasing in fact. Okay, so very good. So here is against the attraction. Follow this. Here attraction. Here overcoming the attraction. Separated. So internal energy increasing in the form of potential energy. Should there be attraction, and there is attraction in real systems. Increase again power in constant pressure process. Again, increase in the constant pressure process again. Over again, right, for unit rising temperature as before. For unit rising temperature, don't forget, because definition is unit rising temperature of heat capacity. Question is what? How much heat for unit rising temperature? This is the question. Which requires more heat? Follow. Cp minus Cv. Follow. One line. Which requires more heat for unit rising temperature? Constant pressure, which requires more heat for unit rise in temperature. Both cases unit rise, same rise. Which requires more heat? Answer, first law says, these are the, address these two. 3, address these two. See in which case dW is there. Work done is there. Yes, sir, in case of volume change is there. There is no volume change, no work, no nothing. So volume change, yes, sir, work done term is there. So accordingly, dQ will be required more. And then when there is expansion, another feature is coming. This is overcoming the intramolecular attraction and increasing the potential energy. Means internal energy. So see, this term is addressed, this term is addressed by these two terms. You split this. That's it. That's it. Constant pressure for unit rise in temperature as required in the definition like before. I am not writing this. Why unit rise? The definition is what? Heat required. Tell. Heat required to raise the temperature of a body through unit degree. Over, and then this is the last line. Then this is the last line. I've said. Now, special case. Now, special corollary. Can I remove this? Special case. Special case is who? 5 minutes. Over. Special case. Let us. And it is one line. Special case is what? Tell me, guess. Ideal gas system. Ideal gas as. Tell me. Ideal gas. Now this let me complete quickly. Ideal gas as system. This is ideal gas as system. What is the specialty of ideal gas? What is this value? Du dV at constant temperature.